Welcome to today's problem walkthrough. We'll be tackling problem number 829, titled Consecutive Numbers Sum. This is an interesting mathematical problem that challenges us to find how many ways a given number can be expressed as the sum of consecutive integers. Let's dive in. The problem we're solving is called Consecutive Numbers Sum. The goal is to determine how many ways we can express a given integer, n, as the sum of one or more consecutive positive integers. For example, if n equals 5, we are tasked with finding all possible sequences of consecutive numbers that add up to 5. The input is an integer n, where the value can range from 1 to 10 to the power of 9, and the output is another integer that tells us the total number of valid ways to represent n. In the first example provided, we have an input n equals 5. The output is 2, which means there are two distinct ways to write 5 as a sum of consecutive integers. To understand why the output is 2 when n is 5, let's look at the possible representations. The first is simply the number 5 itself, which counts as a valid sequence. The second representation is the sum of two consecutive numbers, 2 plus 3. Together, these give us the two valid ways to express 5. In another example, where the input is n equals 9, the output is 3, meaning there are three ways to write 9 as a sum of consecutive positive integers. Now, let's break down the reasoning for n equals 9. The first way is to consider 9 as a single number, which is always a valid representation. The second way is to write it as 4 plus 5, which is the sum of two consecutive integers. Finally, the third way is to write it as 2 plus 3 plus 4, which includes three consecutive integers. These three representations explain why the output for n equals 9 is 3. As another example, we are given n equals 15, for which the output is 4. This means there are four ways to represent 15 as a sum of consecutive integers. For n equals 15, let's look at these four representations. First, we have the number 15 itself, which counts as one way. Next, we can write it as the sum of two consecutive numbers, 7 plus 8. A third valid representation is 4 plus 5 plus 6, which is the sum of three consecutive integers. Finally, the fourth way is to write it as 1 plus 2 plus 3 plus 4 plus 5, which involves 5 consecutive integers. Together, this gives us a total of 4 valid ways to express 15. It's important to note that the constraints of this problem require the solution to handle values of n up to 10 to the power of 9 efficiently. For smaller values like n equals 1, the only possible representation is 1 itself. For prime numbers, the result will always include the number itself but may also include other valid sequences. To solve the problem of finding how many ways we can express a number as the sum of consecutive integers, we first considered a brute force approach. The idea here is intuitive: try every possible starting point, denoted as k, and calculate the sum of consecutive numbers starting from k until the sum either matches the target number n or exceeds it. This can be implemented by iterating over all potential values of k, and for each value, summing up numbers incrementally. However, this method has significant drawbacks. The time complexity can reach n squared, in the worst case because we may need to compute sums for a large number of starting points. This makes it computationally expensive for large inputs, especially since n can go up to 10 to the power of 9. While the space complexity is efficient at 1, the brute force approach becomes impractical due to its inefficiency for large values of n. Therefore, we need a more optimized solution, which brings us to the mathematical approach. The mathematical approach provides a significant optimization by leveraging the structure of the problem. Instead of testing every starting point, we focus on the length of the sequence, denoted as x. Using the formula for the sum of consecutive integers, we can rearrange the equation into a form where k, the starting integer, is expressed in terms of x. Specifically, k equals n x asterisk x1 / 2 / x. For k to be a positive integer, the numerator must be divisible by x. This insight reduces the problem to finding values of x where this condition holds. Importantly, we only need to check values of x such that x asterisk x1 / 2 is less than or equal to n, which drastically limits the range of possible values for x. The implementation is straightforward: we iterate over these possible values of x, check the divisibility condition, and count the valid values. This approach has a time complexity of sqrt 2*n as the constraint limits the iterations to the square root of n. The space complexity remains 1, and overall, this method is highly efficient, even for very large inputs. While there is an alternative factorization-based method, the mathematical approach is chosen for its simplicity and speed. The mathematical approach was selected as the optimal strategy for several reasons. First, it aligns closely with the problem structure, targeting the constraints directly. This approach focuses on iterating over potential sequence lengths, denoted by x, and checking if the conditions for divisibility are met. The implementation is clean and avoids unnecessary computations, making it a faster and more practical solution for large values of n. Compared to the brute force method, the mathematical approach dramatically reduces the time complexity from n squared to sqrt n, which is a crucial improvement for handling inputs as large as 10 to the power of 9. It also avoids the additional steps required in the factorization approach, where divisors of n need to be computed. This makes the chosen method simpler and more direct. One key insight, or aha moment, in this approach was realizing that the problem reduces to finding valid sequence lengths x that satisfy the divisibility condition n x x1/2% x == 0. This insight reframed the problem in terms of manageable iterations, eliminating redundant calculations and making the solution highly efficient. Overall, this strategy not only addresses the specific problem effectively but also generalizes well to similar problems involving sums of consecutive integers. To begin, the problem asks us to determine if a given positive integer, n, can be expressed as the sum of two or more consecutive positive integers. If such a sequence exists, we need to return it, otherwise, we should indicate that no valid sequence can be formed. One straightforward way to approach this is with a brute force method, where we systematically test all possible sequences starting at different integers to see if any sum matches n. We initialize by setting the starting integer, k, to 1, and preparing a variable called current_sum to keep track of the total as we build each sequence. For every potential starting point k, ranging from 1 up to half of n, we attempt to form a sequence. This range is chosen because any starting point beyond n/2 would make it mathematically impossible to form a valid sequence with two or more terms. At the start of each attempt, we reset the current_sum to 0 and initialize an empty list sequence to store the integers being tested as part of the current sequence. Once we have our starting point k, the next step is to form a sequence. This involves adding consecutive integers to current_sum, starting from k. Each integer we add is also appended to our sequence list. After each addition, we check whether the sum equals n. If it does, we immediately return the sequence, as we've found a valid solution. On the other hand, if the current_sum exceeds n at any point, we can stop the process for that starting point since it's clear that no valid sequence can be formed. The loop for that k is broken, and we move on to the next potential starting point. If, after iterating through all possible starting points, no valid sequence is found, we simply return a message indicating that no solution exists for the given n. This approach ensures that all possibilities are considered while minimizing unnecessary computations. There are several key insights that help us understand the behavior and limitations of this brute force approach. First, the search space is finite, as the starting point k must always be less than n/2. This is because sequences with starting points higher than this would exceed n after just one or two terms. Second, the algorithm is designed to exit early whenever the sum exceeds n. This provides an efficiency boost by preventing redundant calculations for sequences that are guaranteed to fail. Finally, there's an important mathematical insight that can guide us toward potential optimizations. The sum of a sequence starting at k and containing m terms can be expressed with the formula s equals m*k plus m*m1/2. While this formula isn't directly used in the brute force solution, it lays the groundwork for a more optimized approach by providing a direct mathematical relationship between the sequence parameters and n. The brute force algorithm relies on simple data structures to keep track of the ongoing computations. Specifically, a list is used to store the current sequence of integers being tested. This enables easy validation and output if a matching sequence is found. Additionally, we use two key variables, current_sum, which tracks the sum of the integers in the sequence as we build it, and sequence, which stores the specific integers being tested at any given time. These lightweight data structures ensure that the algorithm is straightforward to implement while maintaining clarity and functionality. To make the process more efficient, there are several optimizations we can introduce. First, instead of iterating through sequences, we can use the mathematical formula for the sum of a sequence to calculate the number of terms, m, algebraically. By rearranging the formula to solve for the starting point k, we reduce the need for repetitive iterations. Additionally, we can perform a quick pre-check for evenness. Some even numbers cannot be expressed as the sum of consecutive integers, so identifying these cases early allows us to skip unnecessary calculations. Lastly, we can optimize further by only considering divisors of n as potential candidates for k. This dramatically narrows the search space since divisors provide a natural way to partition n into potential sequences. Now, let's analyze the complexity of the brute force approach. In the worst case, the time complexity is O(n), as we iterate over all potential starting points up to n//2. For each starting point, we may need to compute sums of sequences, which adds to the overall cost. The space complexity is O(m), where m is the length of the sequence being stored. To illustrate the algorithm in action, let's consider an example. If the input is n equals 15, we start with k equals 1. The sequence formed is 1, 2, 3, 4, 5, which sums to 15. Since this matches the target, we return the sequence. For another input, say n equals 10, we again start with k equals 1. The sequence, 1, 2, 3, 4, sums to 10, so we return it as the solution. If we continue testing for n equals 10 with the next starting point, k equals 2, the sequence formed is 2, 3, 4, which sums to 9. Since this is less than 10, we cannot use this sequence as a solution. We would then move to the next starting point and continue this process until either a valid sequence is found or all possibilities are exhausted. This example highlights how the algorithm systematically explores each potential sequence and efficiently discards those that cannot work, ensuring we arrive at the correct result without unnecessary calculations. The provided solution determines how many different ways a positive integer n can be expressed as the sum of two or more consecutive positive integers. Here's how the code works. 1. Initialize variables. Count is initialized to 0. This variable will keep track of the number of valid sequences found. K is initialized to 1. This represents the length of the sequence being tested. 2. Iterate over sequence lengths. The while loop runs as long as the sum of the first k integers, given by k asterisk, k plus 1, //2, is less than or equal to n. This ensures we only consider sequence lengths that are feasible for the given n. 3. Check divisibility. For each sequence length k, the code checks if the remaining value, n k asterisk, k plus 1, //2, is divisible by k. If it is, this means a valid sequence exists for this k. If the condition is met, count is increment. For increment sequence length, the value of k is increased by 1 to test the next possible sequence length. 5. Return the result. After the loop completes, the total number of valid sequences is stored in count, which is returned as the result. ###key insights. The formula k asterisk, k plus 1, //2 gives the sum of the first k integers. This is subtracted from n to determine the remaining value that must be evenly distributed across the sequence. The conditions in k asterisk, k plus 1, //2, %k equals 0 ensures that the remaining value is divisible by k, confirming the existence of a valid sequence. ### complexity. Time complexity, n, as k grows linearly and the loop runs until k asterisk, k plus 1, //2n. Space complexity, 1, as no additional space is used beyond a few variables. This approach efficiently calculates the number of valid sequences without explicitly generating them, making it highly optimized for large values of n. This is the Java implementation of LeetCode problem number 829, consecutive number sum. The logic mirrors the Python implementation, using a loop to check all possible lengths of consecutive sequences, k, that sum to n. Key differences include Java's explicit type declarations and the use of integer arithmetic. The solution determines if a valid sequence exists for each k by ensuring the remaining value after subtracting the sum of the first k natural numbers is divisible by k. To solve this problem, we start with an example where n equals 15. First, we initialize two variables, count, which is set to 0 to track the number of valid sequences, and k, which starts at 1 and represents the length of the sequence we are checking. For the first iteration, when k is 1, we compute the sum of the first k natural numbers using the formula k asterisk, k plus 1, slash 2, which gives us 1. Since 1 is less than or equal to 15, we proceed to check the next condition. Here, we calculate the remainder when any k asterisk, k plus 1, slash 2 is divided by k, substituting the values, 15 to 1, % 1 equals 0, meaning the condition is satisfied. As a result, we increment count to 1 and increase k to 2 to evaluate the next sequence length. With k now equal to 2, we calculate the sum of the first k natural numbers using the same formula, which gives 2 asterisk 3 slash 2 equals 3. Since 3 is less than or equal to 15, we proceed to check if any k asterisk, k plus 1, slash 2, % k equals 0. Substituting the values, 15 to 3, % 2 equals 0, so the condition is satisfied. We increment count to 2 and then increase k to 3. Next, with k equal to 3, we compute the sum as 3 asterisk 4 slash 2 equals 6. Since 6 is less than or equal to 15, we check the condition again. Here, 15 to 6, % 3 equals 0, so the condition is satisfied. We increment count to 3 and set k to 4. When k is 4, the sum of the first k numbers is 4 asterisk 5 slash 2 equals 10. Since 10 is still less than or equal to 15, we check the condition, and k asterisk, k plus 1, slash 2, % k. Substituting the values, 15 to 10, % 4 equals 0, so the condition is satisfied. We increment count to 4 and increase k to 5. Now, for k equal to 5, the sum becomes 5 asterisk 6 slash 2 equals 15. Since 15 is equal to n, we check the condition once more. Here, 15 to 15, % 5 equals 0, so the condition holds, and we increment count to 5. When we move to k equal to 6, the sum becomes 6 asterisk 7 slash 2 equals 21, which exceeds 15. At this point, the loop terminates because we know no further sequences are possible. After completing all iterations, we find that the total number of sequences for n equals 15 is 5. Now, let's examine another example where n equals 9. We begin by initializing count to 0 and k to 1. For the first iteration with k equal to 1, the sum of the first k numbers is 1 asterisk 2 slash 2 equals 1. Since 1 is less than or equal to 9, we check the condition, and k asterisk, k plus 1, slash 2, % k. Substituting the values, 9 to 1, % 1 equals 0, so the condition is satisfied. As a result, we increment count to 1 and increase k to 2. Next, with k equal to 2, we calculate the sum of the first k numbers as 2 asterisk 3 slash 2 equals 3. Since 3 is less than or equal to 9, we check the condition, and k asterisk, k plus 1, slash 2, % k. Substituting the values, 9 to 3, % 2 equals 0, so the condition holds. We increment count to 2 and increase k to 3. For k equal to 3, the sum becomes 3 asterisk 4 slash 2 equals 6. Since 6 is less than or equal to 9, we check the condition again. Here, 9 to 6, % 3 equals 0, so the condition is satisfied. We increment count to 3 and set k to 4. For k equal to 4, the sum becomes 4 asterisk 5 slash 2 equals 10, which exceeds 9. Therefore, the loop terminates. At the end of the iterations for n equals 9, we determine that the total number of valid sequences is 3. Finally, let's analyze one last example where n equals 5. We start by initializing count to 0 and k to 1. For the first iteration, with k equal to 1, the sum of the first k numbers is 1 asterisk 2 slash 2 equals 1. Since 1 is less than or equal to 5, we check the condition, and k asterisk, k plus 1, slash 2, % k. Substituting the values, 5 to 1, % 1 equals 0, so the condition is satisfied. We increment count to 1 and increase k to 2. For k equal to 2, the sum of the first k numbers is 2 asterisk 3 slash 2 equals 3. Since 3 is less than or equal to 5, we check the condition nk asterisk k plus 1 slash 2% k. Substituting the values 5 to 3, % 2 equals 0, so the condition holds. We increment count to 2 and set k to 3. For k equal to 3, the sum becomes 3 asterisk 4 slash 2 equals 6, which exceeds 5. At this point, the loop terminates. Finally, we conclude that the total number of valid sequences for n equals 5 is 2. To analyze the time complexity of this algorithm, we first consider how the loop iterates over potential lengths of consecutive integer sequences, represented by the variable k. The condition for the loop to continue is that the sum of the first k natural numbers, given by k asterisk, k plus 1, / 2, must be less than or equal to n. Since this sum grows quadratically with respect to k, solving the inequality k asterisk, k plus 1, / 2 equals n gives us approximately k equals O, sqrt, 2n. This means the loop executes in O, sqrt, n iterations. Within each iteration, the algorithm performs a few basic arithmetic operations like subtraction, division, and modulus checks, each of which takes constant time, or O1. Therefore, combining the O, sqrt, n loop iterations with the O1 operations in each iteration, the total time complexity of this algorithm is O, sqrt, n. The space complexity of the algorithm is straightforward to evaluate. The input parameter n is passed to the function but does not incur any additional space usage. The algorithm uses a few auxiliary variables, such as count to store the number of valid sequences and k to track the current sequence length. These are simple integer variables, and their space usage is constant, or O1. Importantly, no extra data structures like arrays or lists are introduced, so the space usage remains minimal. Taking all this into account, the overall space complexity of the algorithm is O1. When comparing this optimized approach to a brute force solution, the efficiency gains become evident. A naive method would involve iterating over all possible starting points and lengths of sequences, manually summing the numbers in each case to check if they equal n. This would result in a time complexity of O, n, in the worst case, due to the repeated summation calculations for each possible sequence. In contrast, the optimized approach leverages the mathematical formula for the sum of consecutive integers, k asterisk, k plus 1, / 2, to eliminate the need for redundant summations. By reducing the number of iterations from O, n, to O, sqrt, n, and performing only constant work per iteration, the current solution is significantly faster and more efficient. Analyzing the algorithm across different cases, we observe that the time complexity consistently remains O, sqrt, n. In the best case, for small values of n, the loop terminates quickly as the value of k reaches O, sqrt, n, rapidly. In the average case, for any arbitrary value of n, the same formula applies, and the algorithm performs the same operations within the O, sqrt, n iterations. Even in the worst case, for the largest possible value of n, the number of iterations is still bounded by O, sqrt, n. This uniformity arises because the sum of the first k natural numbers grows quadratically, and solving the inequality k asterisk, k plus 1, / 2 equals n consistently yields k equals O, sqrt, n. Since each iteration involves constant time operations, the overall complexity is O, sqrt, n. Additionally, because no extra space is used beyond a few variables, the space complexity remains O1. In summary, the algorithm achieves a time complexity of O, sqrt, n, and a space complexity of O1. By relying on mathematical formulas instead of brute force summation, it minimizes unnecessary computations and optimizes performance. This makes it a highly efficient solution for the problem of finding the number of ways to represent n as a sum of consecutive integers. When solving this problem, there are several common mistakes to watch out for. First, overlooking edge cases is a frequent issue. For example, failing to handle the smallest inputs, such as n equals 0 or 1, or even invalid inputs like negative numbers, can result in runtime errors or incorrect outputs. Accounting for these edge cases ensures your solution is robust under all test conditions. Another common pitfall is relying on an inefficient brute force implementation. This typically involves iterating through all possible starting points and summing integers naively, ignoring opportunities for optimization. While this approach might work for smaller inputs, it becomes untenable for larger values of n, such as numbers greater than 100,000. Finally, incorrect termination conditions are another source of error. If your loop stops too early or runs longer than necessary, it can lead to missed valid sequences or redundant computations. Both of these consequences impact the efficiency and correctness of your solution. Another area to be cautious about is the misuse of arithmetic progression formulas. The sum of consecutive integers can be represented using a formula, such as k times the average of the start and end values. However, forgetting or misapplying this formula can lead to unnecessary calculations and incorrect results. Precision errors are also a risk when performing floating-point arithmetic. For instance, if you use floating-point operations instead of sticking with integers, you may introduce small but significant inaccuracies, especially when working with very large values of n. To avoid these issues, it's generally better to stick with integer arithmetic, which is both precise and efficient. In interviews, it's crucial to focus on identifying patterns within the problem. For example, recognizing that the sum of k consecutive numbers can be expressed as a formula allows you to avoid repeated summations and simplifies the process considerably. You should also consider the constraints of the problem. For large inputs, brute force approaches are rarely viable, so mathematical optimizations are preferable. Be ready to justify your chosen approach, whether it's a formula or an iterative method, and explain how it impacts time complexity. For instance, using a formula reduces the complexity from n squared to n, or better. Additionally, interviewers appreciate candidates who think about edge cases and explain how their solution handles them. This demonstrates a thorough understanding of the problem and a commitment to ensuring correctness under all scenarios. There are several related problems that can help you build a stronger understanding of consecutive sums and similar concepts. For instance, LeetCode problem 829, the consecutive numbers sum problem, is a direct variation of this challenge, focusing on finding how many ways you can express n as a sum of consecutive integers. LeetCode 1, the two-sum problem, involves finding two numbers in an array that add up to a target, which is another summation-based challenge. LeetCode 560, subarray sum equals k, extends this idea by requiring you to find subarrays within an array that sum to a specific value, often utilizing prefix sums or sliding window techniques. Finally, LeetCode 1493, longest subarray of ones after deleting one element, explores sequences and sums under additional constraints. Working on these problems can deepen your understanding of how to approach summation and sequence-related challenges effectively. When it comes to solving this problem, there are several alternative approaches to consider. A straightforward option is brute force, where you test all possible starting points and some consecutive integers. While simple to implement, this method has a time complexity of n squared, making it inefficient for large values of n. A more efficient alternative is using a mathematical formula to calculate the target sum directly. This approach drastically improves performance, achieving a complexity of n, or better, but it does require a solid understanding of the underlying formulas. For very large input sizes, binary search can be a powerful tool. By narrowing down the search space and combining it with mathematical checks, you can identify valid sequences more efficiently, though this method is more complex to implement. Lastly, techniques like sliding windows or prefix sums are excellent for array-based variations of this problem. These methods optimize the process of finding subarrays that meet specific criteria, but they may not directly apply to simpler versions of the problem. Each approach involves trade-offs, so it's essential to choose the one that best fits the problem's constraints and requirements. Great job on completing this problem walkthrough. We covered the consecutive sum problem, explored its brute force approach, and highlighted key takeaways. Keep up the practice, and don't forget to like and subscribe for more problem-solving content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!